really quite honored to be spending this time with you tonight. This is a real pleasure of mine. And tonight, just like Stacy said, I really want to share the story of a teeny tiny moon of Saturn called Enceladus. It's a world that maybe few or less people have perhaps heard of, but one that I really think might offer us some of the best chances of finding life beyond Earth, and really helping answer one of humanity's oldest and most fundamental questions of whether or not we are the only living planet in the universe. But before we dive into that, before we dive into these big fundamental questions, let me just introduce myself. So like Stacy mentioned, my name is Erin and I am an astrobiologist. I'm currently doing my postdoctoral work at the NASA Goddard Space Flight Center. And as an astrobiologist, I spend my days really contributing to this long-standing search for life on other worlds. And I particularly focus on bodies within our solar system, so ones that we have an opportunity to directly observe with our spacecraft and directly investigate with our robotic assets. And so my path to NASA really began with geology. I'm fundamentally trained as a geologist, so I go outside and I study rocks and minerals, and I look at the stories that are recorded in those rocks and minerals about Earth's history. And I specialized in a subtopic called biogeochemistry, so the organic chemistry of biology as it's recorded in rocks. And so I really studied how to interpret chemical signatures of what life leaves behind. And often when I try to explain really what I do, I like to ask people to think about how paleontologists, we often use like dinosaur fossils, right, or seashells to understand the history of life on Earth. And these fossils, these bones and teeth and shells, they work really great because complex animals have hard parts. They have bones, they have shells, they have teeth that can be preserved in rocks for millions of years in really pristine states of preservation. And we can read what those animals might have looked like in the past. But when we start thinking about astrobiology, when we think about life that might have existed on other planets, we're really not expecting to find life forms like dinosaurs or fish or sharks. We're most likely looking for things that are very small, like microbial life. We're talking about bacteria, maybe viruses, something like an archaea. And we think that this makes sense because when we consider the history of life on Earth, we've got a little timeline with today on the right here, where humans have evolved all the way back in time to when Earth formed about 4.6 billion years ago. And you can see for the majority of that timeline, the bulk of Earth history, the life on this planet has been dominated by very teeny tiny microscopic organisms. They started single cellular, they eventually evolved into multicellular complexity, but life has almost been exclusively microbial for the majority of Earth's history. And so when we think about looking for life on our other planets, it makes a lot more sense to look for signs of life that correspond to these kind of creatures. If they dominated our planet, it makes sense that they might have dominated other planets, especially because on our planet, we find these microorganisms in extreme environments. We find them at the bottom of the ocean under high pressures. We even find them very close to volcanic centers at extremely high temperatures in radiated environments. These kind of organisms are extremely hardy. They're resistant. They're the kind of organisms we really expect to be finding in these extreme environments on other planets, not the kind of like charismatic macrofauna like a lion or a tiger or a bear that we see in nature documentaries. We're looking for microbial life. But the challenge is, how do you fossilize a microorganism? We're not getting bones, we're not getting fossilized teeth. These organisms don't have any of those hard parts. They don't have bones or shells to fossilize the way that a dinosaur would. And so what I do is I try to look at these kind of non-traditional fossils. And this is where the idea of a chemical fossil comes in. And this is why I'm a biogeochemist. So I look for the molecular fingerprints, really the specific chemicals that we know that only life makes. And if those chemical markers can get locked into rocks, just like a dinosaur bone can, then they can be preserved for billions of years. Long after the microbes themselves have died and decayed, they leave behind these chemical traces that I can extract and look at in the kind of laboratory that we have at NASA. And so I've spent my career so far trying to understand what these signatures of microorganisms look like and defining what chemical fossils we might encounter on other worlds. And so now I do spend my time, I think about these other worlds and I look at space and I work on the problem of whether or not there is life on Earth and what might that life look like, what kind of chemical fossils would it leave behind, and really critically, where are we most likely to find these fossils? It can be extremely expensive to send a spacecraft to another world. And so we want to be sure that we are looking in places that give us the maximum likelihood of finding the answers to the questions that we're asking. And so today I really want to bring to your attention a world that I think has a huge amount of potential for future investigation. And it's a world that has captured the attention of astrobiologists, so my colleagues, my contemporaries. It's really excited people recently. And this all started back in the summer of 2005, so just over 20 years ago. This was really before my career started, but I've been following it in recent years. And that's when NASA discovered this tiny little diminutive moon of Saturn. And it's called Enceladus. You can see it on your screen there on the left. It's this teeny tiny little feature. And they discovered, and we'll talk about this a little bit later, but they discovered a warm liquid water ocean that's theoretically capable of supporting life. And that was unlike anything the scientists at the time, this is 20 years ago, were anticipating to find that far out in the solar system. And this is because for decades, planetary scientists had really focused on what we call like the Goldilocks zone. And this is that sweet spot around a star, so around our sun, that's not too hot. If we're too close to the sun, we're too hot and everything's molten or melting or vaporizing, and also not too cold. Otherwise, everything's just frozen. And we really think that life requires liquid water. And so if we're frozen, we don't really have life. And so this really left us for a long time just considering planets like Venus, which turned out to be extremely hot at the surface, and planets like Mars, our nearest neighbor. It's pretty cold, but we think it might have had a warmer past. And so maybe some liquid water, maybe the potential for life. But we really kind of constrained our vision to this Goldilocks zone since we know that life needs water. And this is the only place that water is really stable in our solar system. But it turns out that there's other physical phenomena that we're still studying, we're still discovering at NASA that can heat up moons of some of these distant worlds far out in our outer solar system. We're now calling these things ocean worlds. And I have a little diagram here. You can see that they're icy moons, they're ice on the outside. But underneath, they harbor these massive liquid water oceans underneath that frozen shell, like an eggshell with a liquid water ocean inside. And the key insight here is that these things, they're not heated up by the heat from the sun. They're heated by the gravitational forces of their massive parent planets like Jupiter and like Saturn. And we've now discovered several of these ocean worlds. They're not a rare phenomenon. We've discovered things like Europa and Ganymede around Jupiter. We've got Titan and Enceladus around Saturn, and other ocean worlds like this within our solar system. But for me today, what we're really going to be spending our time on is that Enceladus world around Saturn. And I really think it offers like the most fascinating astrobiological potential of all of the ocean worlds we found. This is my opinion. I think it's the coolest moon in our solar system, and I'm so excited for us to study it. And NASA is really considering a follow-up mission to Enceladus, potentially within the next decade. And so that's why I thought it was the perfect time for us to spend some time tonight talking about this really cool moon. So if we dive into Enceladus, let's think about Saturn for a second. So in our solar system, Saturn is probably the most blessed in riches when it comes to having moons. It has 274 moons orbiting Saturn. These are all often quite small. Sometimes we call them moonlets, but 274 moons. Can you imagine looking in the sky and seeing 274 moons? And although this is not about Enceladus, this is not totally relevant to today's topic, but whenever I mention Saturn's rings and Saturn moons, I really like to share these incredible photos that were captured by NASA. And what you're seeing here, this is a close-up of Saturn's ring. And that little feature, if you can see my arrow, that little round feature kind of near the bottom right corner, that's one of Saturn's moons. And it's it's carving out space in that ring, and it's leaving behind ripples in the ring of Saturn, almost like the wake behind a boat traveling through the sea. And I think it's so incredible to think about these little moons transiting around Saturn, leaving ocean-like waves drifting in Saturn's rings. I just think that's such a beautiful concept. But anywho, back to Enceladus. So Enceladus is one of these wonderful moons that's orbiting Saturn. It is the sixth largest of Saturn's moon, but it's still quite small. It's about 1/7 the size of our moon. It's only 315 miles across. And so to put that in perspective, if we think about the United States, we think about the country we're in, Enceladus could really easily fit pretty much within the state boundaries of Arizona, whereas our moon would take up the entire face of the continental United States. So very different size scales here. But even though Enceladus is so small, I named my talk Tiny Moon, Big Questions. Even though it's diminutive in size, it is so intriguing. It's just spectacular. And the first fascinating thing about Enceladus is it is the most reflective object in our solar system. It's the whitest, it's the brightest thing in our solar system, other than the sun. The most reflective body. And this is because Enceladus reflects back nearly 100% of the sunlight that falls on its surface, making it about as bright as like fresh fallen snow, pure ice. And to put that into context again, that our moon, when we look up at the night sky in our moon, it's only reflecting back about 12% of the sunlight. And so it might look bright to us on a clear night, but that's only because the sky is dark. If we put Enceladus in our night sky at the same distance as our moon, it would light up our night so brightly we could go outside and read a book on a full moon night. That's so cool. So our moon is dull in comparison. Enceladus is bright white. It reflects almost all the light that falls onto it. But the reason that it is that bright is what makes it really, truly spectacular. Enceladus, you can see in this photo, it's covered in ice. But just being icy doesn't mean that it should reflect all of its light. The solar system is a pretty dirty place. We've got a lot of dust. We've got a lot of rocks. These would be perpetually falling on the bodies in our solar system, and they should make that ice look dusty over time. And so what this told us, this was kind of the first sign that Enceladus was an interesting body in our solar system. This really told us that there has to be some kind of process that cleans the surface or puts a fresh coating on that surface pretty regularly, because we're not seeing an accumulation of dust. So there has to be fresh material on that surface. This is a geologically active moon all the way out around Saturn, and it's tiny. That process really remained a mystery until the early 2000s. And in the I meant to show this. Something must be refreshing the surface. But we didn't figure out this question, like what was refreshing the surface of Enceladus, until we sent this spacecraft out to Saturn. And so this is an artist conception of what the spacecraft looked like as it orbited Saturn. This is the Cassini-Huygens spacecraft, and it's a cooperative project. It was put together by NASA, the European Space Agency, and the Italian Space Agency. They came together and they built this mission. And it was really designed to study the composition of Saturn's, its ring dynamics, and look at some of the moons. And when it flew by little Enceladus, this was back in 2005, when the Cassini mission flew by Enceladus, it saw something just simply extraordinary. This was some of the original photos. And you see at the bottom, coming out of the south pole of Enceladus, the scientists at times, they observed these massive jets just erupting from the surface of this moon and venting into space. We're talking like massive plumes of material coming out of this moon, just shooting into the vacuum of space like cosmic geysers. It was incredible. And some of those particles, it turns out that it's water and ice and dust that's coming out of this moon. And some of those particles actually rain back down on the surface of Enceladus like snow. It's like a extraterrestrial outer solar system blizzard that covers the surface of the moon in fresh snow, and it keeps it bright and white and clean and free of dust. And it's the reason that it's the most reflective body in our solar system. It's so cool. But the material that doesn't snow back down onto the surface of Enceladus, it actually escapes. Enceladus really does not have a lot of gravity, so a lot of that material escapes the gravitational influence of Enceladus. And what it does is it actually builds up one of Saturn's rings, one of the incredible rings of Saturn that we can see with telescopes right from here on Earth is actually made of the water and ice that is venting out of the south pole of Enceladus. And I just think that's so cool. But remember, at this time, we're 20 years ago, the Cassini-Huygens mission planners, the people who put this mission together to explore Saturn, they had no idea that they were going to find an icy moon of Saturn that was spewing massive amounts of water into space. They weren't expecting to find it, and they certainly weren't expecting to be able to sample that. But the discovery of all of this water being vented into space, it was like pandemonium amongst the scientific community. We knew we had to sample this material. This was the most incredible thing we had seen. It was totally unexpected. Again, we did not expect to have liquid water this far out in the solar system. And so the spacecraft managers, what they did is they rejigged the mission. They changed the schedule of the Cassini-Huygens orbital path so that we could fly through those geysers coming out of Enceladus. This is another artistic impression. This is showing what it might have looked like when the Cassini spacecraft flew through those geysers of Enceladus. And what it was able to do, if we look at the spacecraft here, there was a little instrument on the side on board to the Cassini-Huygens spacecraft. This is called the Cosmic Dust Analyzer. This instrument was designed to look at interplanetary dust particles on its transit to Saturn. But they were able to use this instrument to capture the ice grains that were coming out of the Enceladus plume. So this instrument, it was designed to take dust grains in space. They would get collected kind of in this little cup. And when they hit the metal at the back of that cup, they're hitting it at extremely high speeds. And so these tiny particles, they would slam into that metal target. And it was at speeds that were high enough to pretty much instantly vaporize those particles that were coming in. So they were able to turn that cloud of turn the particles into charged atoms that then the instruments on board they could sniff, they could taste that atomic cloud, so these charged particles, and they could figure out what they were made of. It's like a taste test. You could tell whether the instrument had tasted like dust or water, whether that water was fresh water or salt water or something else entirely. And so by flying the spacecraft through those plumes and collecting the particles that were coming out of Enceladus, coming out of this moon, the scientists were able to start understanding what was coming out, what was the composition. And so what they discovered is one of the first things that they saw was what was coming out was mostly water ice. And it was coming out of 4 giant cracks in the ice shell of Enceladus. It had looked like the south pole of Enceladus had cracked open and water ice was coming out. It was spewing into space. And then they made the incredible discovery that some of those particles, it wasn't just water, they actually detected small amounts of salt. And these were things like sodium chloride, which we know is table salt, along with potassium and some other minerals. And this was like the first concrete evidence that the water vapor that we were seeing, it's not just evaporating from the ice on Enceladus's surface. This is actually tapping directly into a liquid, salty ocean underneath the ice. And they were able to understand the chemistry. They think it's a little less salty than the oceans that we have on our seas, a little bit more alkaline. But we've got a salty ocean orbiting Saturn. That's so cool. And then in about early 2015, so 10 years ago, there was another breakthrough discovery. They detected small amounts of microscopic silica. So this is the stuff that makes up like quartz and sand. And they found small amounts in those water particles that were coming out of Enceladus. And what made that really exciting, that was really intriguing for scientists. And they did some experiments back here on Earth in the laboratory. They took a bunch of rocks, they reacted them with water, and they found that one of the only ways you get microscopic, like nanoparticles of silica, is if you boil your water up to around 90 degrees. And so that was the first evidence of hot water chemistry beyond Earth, anywhere in our solar system. And that was incredible because that told us that Enceladus doesn't just have an ocean underneath its ice gel. It has a hot hydrothermal floor. It's got it's got vents, hydrothermal vents on its seafloor that's heating the water, circulating the water, causing chemical reactions. And when we think about this, we have those same kind of ecosystems on the bottom of our oceans. And on Earth, these are incredibly rich, vibrant ecosystems. They're full of nutrients. They're full of life. We think these might be some of the most diverse ecosystems on our planet. It could have been where life formed on our planet. So the fact that we see this on an extraterrestrial body, the implications are just staggering. And then lastly, so going back, so we've got water, we've got salt, we've got hydrothermal activity, and then we started discovering there's nutrients in the water. There's all the elements that we think life needs to really get going and to grow and proliferate, all the key nutrients we think are essential for life. And so suddenly, Enceladus has all of the ingredients of the astrobiological recipe for life. We've got water, we have energy, we have heat, we have chemical elements necessary for life. And then we made another discovery. 2018, scientists report complex organic carbon molecules in these water particles coming out of Enceladus. Now, these large molecules, like I said, this mission that has been studying Enceladus so far, the Cassini-Huygens probe, it was never designed to look at this kind of chemistry. So we know that there are complex, large organic carbon molecules at Enceladus. We don't know what they look like. What I have on the screen here is just a cartoon. It's a hypothesis of what they could look like. But what it tells us is that there is large, complex chemistry. These kind of molecules, this kind of complexity is something that we see on Earth associated with life. It's also something that we see created in those hot hydrothermal vents on the bottom of the ocean. It's also something we see sometimes in meteorites that are all throughout the solar system. And so we really can't tell where these complex molecules came from. We can't say definitively whether they formed from life or from a non-life origin. But we do know that we have complex building blocks of organic chemistry on Enceladus. And so what we can say is we have all the ingredients. Where did I go? Oops. Sorry about that. We can say we have all the ingredients that we think life needs to gain a foothold. And we have the complex chemistry to support it and to potentially support its preservation. I don't know why that's not working. So this makes me really excited about the possibility of life on Enceladus. We have a habitable world and complex organic chemistry. And the astrobiological community, my colleagues, they're really recognizing that this is an incredible potential of this teeny tiny moon of Saturn to host maybe the first evidence of life we could find beyond Earth. And we're really working hard to develop mission concepts that could revisit this planet with spacecraft specifically designed to build on what the Cassini-Huygens mission discovered and to look at that complex chemistry and maybe understand where it came from and start answering those fundamental questions of, is there life here? Are we alone? And so that's the future. The community has really rallied around the concept of going back to this moon with a dedicated mission with astrobiological objectives. This was actually considered the second highest priority for the astrobiological community in a survey that was taken recently. So in the next decade, this is our second highest priority mission objective. And so the community is really coming around, returning to Enceladus to try to answer some of these fundamental questions because we think it has so much potential. And so hopefully if I can come back and give you guys another talk in maybe a couple of years, maybe we'll make some progress on this mission concept. Maybe I'll be able to tell you that we're going to be going to Enceladus. Maybe I can tell you what kind of measurements we're going to take and why I'm so excited about those. But for now, all I can tell you is what we know right now is so interesting. It's so compelling. And I really hope that the future, that that my career might see a mission going to Enceladus, because I'd really like to start digging into some of these science questions that are still open. And that's all I have for you tonight. So thank you all so much for your attention. I really hope you enjoyed learning a little more about my favorite moon in the solar system.